Welcome to NaxToCell. In this video we are showing how to extract results from results files with functions. That at the end of the day is the reason why NaxToCell is used, to be able to post-process the results that are in the results file. We are using the function results for extracting information from results, using function N2C results. If we knew the results file information very well, including IDs of the load cases, the increments that we have, the name of the results that are inside the component that I want, and the sections in which I want to see that component and all the necessary data to obtain the results, we would simply have to add the information that we are asked for. But in this case, we are going to do it through the results file that appears on the screen, and we showed how to create it in video 3. We must be careful when using the N2C results function. It is important to check all the arguments it has. It is a good practice to know first the information included in the file, as we did in previous tutorial, to make sure that when we ask for a kind of information, it actually exists in the file. Because, for example, if we asked for displacements in a load case and that type of result was not asked for when the model run, nothing would come out when using the function. That's why we are going to use the result file that we created in video 3. Here is how to get the results. In this first example we are going to work with results file named bracket.xdb, used previously. We are querying for displacements information. Displacements are results calculated on nodes, so we must select nodes. If we were looking for forces, we would have to select a list of elements, because the results of forces go on the elements. So then, depending on the type of result we are looking for, the list of IDs will have to be nodes or elements. Back to the N2C results function. We select the path of the results file, and displacements as result type. Then, the next thing that is given is a list of load cases and a list of nodes or elements. This option good for, as in this case, is 3, a list of load cases and a list of elements. And then a component is set. The third argument is not a single list, it's a single value. In the end, as you work in Excel, the tables must be two-dimensional. Then, as you have the control option argument of between element IDs or load case node IDs and components, you have to decide which of these two arguments are going to be lists of IDs and which is going to be a fixed value. Because you have to set a value. Otherwise you would produce a three-dimensional table that cannot be represented in Excel 2D tables. Finally, we indicate the load cases. In this case we want to analyze the 6 load cases. We want to see it over the node selected, and we select the list of node IDs over which we want to see results. Once we have selected the previous two arguments, we have to select the component. As previously, we must select only one component to generate a 2 dimensions table. We select magnitude_d, as for the frame is the increment of the results. In a linear analysis there is only one increment. But if we were in a nonlinear or frequency response or eigenvalue analysis, there could be several increments. In any case, if you set one, you always work with the last increment. The rest of the following arguments are optional. Sections argument allows you selecting the sections on which you want to see the results. There are certain results that have sections and other results that do not. For example, displacements are not a type of result connected to sections, but stresses or strengths do. So in that case we would have to decide in which section we want to take results. Now, as we are working with displacements, the default option is none, because in this case this type of result that the displacement are not connected to sections. Superelements argument also by default is 0. In this file we are working with we do not have, therefore, the option is also 0. The next argument would be the average that would be made between the sections, and as there are no sections here does not apply. In grid position would be in case we had a result in a single element. But what we want is to see in the position of the nodes of that element. So, since we are working with displacements, we don't have to fill this section either. The next section is the location level averaging. An example of this would be the average between a node by the value of all the elements that connect to that node. But since offsets are not a value that can be pulled out at the corner of the element, so to speak, it is not applicable either. And the complex format section would be in the case where you're working with a complex result that comes from, for example, a frequency response analysis where you choose whether you want to get the results in real imaginary format or in magnitude and phase format. In the case of displacement and this model, which is a linear static model, it is not necessary. We click on OK and the function automatically calculates the results for the nodes that are marked, which are the ones that have been selected, and for the 6 load cases that were also selected. In the table we get directly the displacements of the list of nodes, for all these load cases. As you can see, the function is pretty fast in accessing and updating information. For example, let's try by changing from magnitude D to the X component, and also changed nodes list. Then click Ctrl plus Shift plus Intro and the function is automatically updated. If you change the list of nodes you choose, you will not see any effect on the table until you extend the matrix. See how can be extended up to node 58. Here ends the explanation of the displacements in the nodes. Next, we are going to show a slightly more complicated example extracting the stresses for the series of elements that we have in the model. Remember that the stresses are results that are applied to the elements, and that certain elements can have different sections within the element. Let's take the list of elements from the file we are working with, in this case the first file. In the first column it is shown the element, in the second the type. The next columns are superelement, property and material. Looking at the table data we see that the superelement 0 property 1, in this case for NASTRAN, does not indicate the material, but for other solvers such as ABAQUS does indicate what is the material. In future versions will also be included for NASTRAN. If we use a filter, we see that the types of elements that we have in the models are C quad 4 ORC tria 3. Next, let's extract stresses. First of all, let's add columns to display the list of results properly. In this case we are going to ask for stresses, so we are going to work with the results file of Model 1 and with the table of element IDs, since stresses are connected to elements. We continue using the function N2C results. We first select the results file. For selecting result type, we could write directly the word stresses, or in this case we use the cell containing the word. In the option argument in this case, we will ask for results of several components in elements for a single load case, because this model only has a single load case. Designing a table in that results will have components as header columns, and elements as rows, so our selection is option 5. Now we select the cells corresponding to components, elements and load case, in that order. As we have said that it is going to give a list of components, we select the components that are shown, which basically are all the components that the model has for the stresses. Then, it gives you a list of elements, for example, the selected ones. Then if you want you can expand it. And you put a load case, in this case one which we know is the only one. Sections. We indicate the value in both Z1 and Z2. You can see that the differences extracting stresses compared with displacements. Now function is using elements instead of nodes, and that now is used the sections argument. The super element is left blank because it is 0. And then we choose the average we want to do between the sections. It is a common practice working with the maximum, so leave it blank for default value unless you are looking for other options. The default value is the maximum, that is, what you get is the value of the stresses in such a component and you get the highest value between Z1 and Z2. The other options are AVG, if you want to get the average, extreme which would be the highest value, the absolute value, and DIFFE, the difference. The last section is the complex format and is useful if you want to get to the element nodes, but for that you would have to request the NASTRAN pass asking for results at the position of the element nodes. In this case it is at the centroid. So, it wouldn't apply, and the mean wouldn't apply either because it's at the centroid and there's only one value. there are not multiple results within the element at different corners or integration points. And with the complex format, it is a linear static pass, there is no complex format. By clicking OK, it is drawn below is the table with the values. To have more clear view, we write the headings of the values. So, what we are getting are stresses components for load case 1 in the list of elements we had selected. You could expand down the selection and pull out many more. For this result we can find the value of the principal angle, the first variant, the maximum, the x component, the xy component, the y component or von Mises, etc. If you expand and select more element IDs, the function only shows the values indicated in the matrix at the selected area. To see the complete matrix, I would have to increase the selection area by doing Ctrl-Shift-Enter. A recommended option if you are in the most modern versions of Excel, is to copy the function as it is, delete the matrix that was so far, re-enter the function, open the wizard and it is calculated to the new area. As shown, all the values of all the stresses of all selected elements of the model appear with all the components for the first load case. Once your sheet is prepared, you can reuse it as much as needed for your benefit. Imagine you have a new results file. Just change the path and file name in your functions and all your sheets will be updated, with no need for additional work. You'll never waste time in getting the results updated in the format you like. We have already gone over the most important functions to extract results, so here ends the video. Hope you find it useful and see you in the next videos.